This is Jupiter, largest member by far of the Sun's family, monarch of the outer planets.
In the late summer of 1977, two unmanned spacecraft, Voyager 1 and 2, lifted off from Cape Canaveral atop Titan Centaur rockets. In the event the spacecraft encounter alien intelligence, both Voyagers carry a copper phonograph record, a message, celebrating the sights and sounds of Earth.
Acting as pathfinder for the Voyagers, Pioneer 11. The 570-pound spacecraft climaxed 6.5 years and a 2-billion-mile voyage in deep space.
Most of what we know about Jupiter comes from one space mission, Galileo, launched aboard the Space Shuttle Atlantis in 1989.
1,000 times the size of Earth.
Larger than 1,300 Earths.
Jupiter is 11 times bigger than the Earth. It's really big.
Big enough to hold over 1,300 Earths.
You could fit about 1,100 Earths inside it.
To our eyes, it reveals only its dazzling cloud tops, rivers of wild color, and its trademark, the Great Red Spot, a perpetual storm of unknown origin. Late November 1973, 20 months after launch, Pioneer 10 closes in on Jupiter. Each hour brings the planet 20,000 miles closer. What lies below those inscrutable cloud tops?
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot. It's slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon.
So, in fact, I said spinning twice as fast as the Earth, it's really fast. That's true, but partly that's because the Earth spins really slow. And the Earth spins really slow for our size because of the Moon, which slows down the rotation.
Nothing's really certain about what's going to happen.
The Pioneers will spend 6 months to a year crossing the asteroid belt, a vast no-man's land of space debris that orbits the Sun between Mars and Jupiter. The asteroid belt is 150 million miles wide. Several thousand asteroids are large enough to be assigned numbers, and some even names. Sizes and numbers of particles will be measured by counting penetrations of these cells. 4 telescopes will observe the brightness, speed, and direction of asteroids.
Jupiter, having the mass and the strength of gravity that it does, makes major perturbations on comet paths, as it did with comet Shoemaker-Levy 9. And it turns out Jupiter actually captured the comet, so that the comet was orbiting Jupiter, and rather than having continued on to orbit the Sun, which it will do if it stayed with Jupiter, because Jupiter, of course, goes around the Sun. But and its close approach was severe enough that the tidal forces just ripped it apart. And comet being what is commonly described as a dirty snowball, if you take a snowball and handle it too roughly, it'll break apart. And coming close to Jupiter counts as being handled roughly, and it broke apart into these many pieces that are hitting in sequence.
I just couldn't believe that we were going to get a chance to see one body in the solar system smash into another one.
We had an up-close and personal view of this unique event.
The comet's name was Shoemaker-Levy 9. As the comet approached, Jupiter's massive gravity tore it to pieces.
This is a Hubble telescope image of Jupiter. Some days before the first impact, we can see the incoming train of 18 or 20 fragments inbound to Jupiter.
Yeah, that's a composite, isn't it?
Yeah.
But that's a beautifully done image that shows a recent Hubble photograph of the comet and a recent Hubble photograph of Jupiter.
It was the gravity of Jupiter that drew the comet in?
Yes. Yeah, you could say that. It was orbiting Jupiter, and one of these orbits it happened to
get too close.
And
pulled in.
That's right. In its previous orbit, it came within 30% of a one Jupiter radius, which was a very close encounter, close enough to break it into pieces.
Yeah, well, the Galileo probe, of course, went into Jupiter. But when we talk about the closest of the spacecraft, we mean in orbit. So Galileo probe wasn't in orbit around Jupiter. This is the closest orbit
that the spacecraft has gone into around Jupiter, and it's considerably closer than Galileo's orbit.
Well, the Galileo mission will orbit Jupiter. It will study its atmosphere. It will carry an atmospheric entry probe that will fall by parachute through the cloud layers.
We have flown through the Jupiter system before, 4 spacecraft. None of them can hold a candle to what Galileo will do, but still, it's not a conceptual novelty, although orbiting a Jovian planet is.
But again, they weren't really in orbit.
This has been a long time coming. I mean, it was a torturous way to get to Jupiter, but we're finally there.
Yeah, well, and you know, given where we were in 1986, where it wasn't clear there was any way to get to Jupiter with Galileo, now it's clear we found a way, and it looks like we're going to be in orbit, and we're going to have a wonderful 2-year tour of the Jovian system.
When we got to Jupiter, we just want to make sure we stay there.
Yeah, that's right.
We're about to jump on that Jupiter train.
Being there, staying there, rather than just flying by with snapshots and a few other bits and pieces of data in a short period of time, we're going to have 2 years at least to really explore at much higher resolution, much greater detail.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown.
What have you learned so far that you didn't know from the telescopic views of Jupiter?
I'm not sure that we've learned any brand new things. We've confirmed many of the ideas that we got from telescopic measurements.
Like what?
Well, we think the fields, we now have a better idea of the radiation belt. We can now tell you in a day or so pretty close the intensity of the fields and the intensity of the magnetic field. We only, from ground-based measurements, could estimate some of these properties.
What influence, if any, does Jupiter have on Earth?
Well, directly, probably very little influence. I think our knowledge of these radiation belts will give us a better idea of understanding our own radiation belts, which do affect the Earth characteristics.
Is that why you wanted to go there?
That's one of the reasons.
School kids are using a radio telescope to collect radio data on Jupiter, and some of that data goes into the model to figure out where the radiation belts are. So we have school kids all over the country running a telescope over the internet, helping us with the radiation belt model. So when you've observed Jupiter, of course, do you want to tell us just a little bit about how you do that and what kind of observations you do with the telescope?
First of all, we connect to the Lewis Center, and then they, thanks to some software, we take the control of the antenna, and thanks of that, we collect the information of the antenna and Jupiter.
Thank you very much.
The background radiation that we're exposed to on Earth is about 1/3 of a rad. What we expect to see at Jupiter is about 20 million rad. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
You always take a risk when you go into an environment like Jupiter's, because you can't really test the spacecraft at the level it's going to be exposed, because you use up too much of its radiation lifetime. So you're extrapolating your experience, saying that it should survive, and the Voyager did survive, although we did have a few little glitches which affected things, not seriously, fortunately.
Jupiter is basically the harshest region in the entire solar system. It is a planet on steroids. Everything about it is extreme. The radiation would just not only kill people, but it would knock out our electronics.
Like the Van Allen belts here on the Earth, only much bigger, because Jupiter's much bigger and the magnetic field's much bigger.
If you think about going back to Pioneer, we really found out what that radiation belt was like there in terms of what we might have to experience with our electronics.
So we need a way to avoid the radiation belts. Previous spacecraft that have gone by Jupiter have done the sensible thing. They've stayed way outside the radiation belts, far from the planet.
And we're going in so close that we're threading a needle between the radiation belts and the atmosphere.
Well, what's interesting about our mission is that every time we fly by the planet, we fly right through the edges of the radiation belts.
Those high-energy electrons are going to fry the electronics of a spacecraft if you fly it through them.
So we went through another set of radiation belts.
And even though we've been studying it literally for hundreds of years, it's one of the very first things anybody ever looked at in the sky with a telescope. And even though you can see it from the Earth, and we've had a spacecraft there,
we have flown through the Jupiter system before. 4 spacecraft. None of them can hold a candle to what Galileo will do, but still, it's not a conceptual novelty, although orbiting a Jovian planet is.
There are still an amazing number of basic questions that we don't have answered about Jupiter, and that's because it's hard.
Just 18 months after launch, disaster struck. Galileo's umbrella-like radio antenna failed to open.
It was beyond devastating. It had to open.
Without that antenna, we thought that the spacecraft would basically not be able to complete its mission.
Back on Earth, NASA engineers scrambled to fix the problem.
There were attempts to jolt it open. They thought perhaps it had just gotten stuck. There were attempts to, kind of go up and down, to try to get it to open.
And I have to say the spacecraft has been performing admirably.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly. The instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter. We're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
Because this was such a critical moment, we turned off all the science instruments right now. When can we expect some science coming back?
A couple of days from now, we'll turn the instruments back on, but our first orbit is 53 days long. And so we come back to Jupiter with all our eyes and ears open the next time. But that's not till the end of August. But we will have spectacular discoveries on that at that time.
As of last evening, 10:47 local time, the spacecraft did go into safe mode, so the science pass was not performed today. All the instruments were turned off as part of the safe mode.
The spacecraft went into safe mode last night, so I'm going to address that. And of course, the delay that we had for our rocket firing, which was originally planned. And then I'll go into the fun stuff, the science.
No problem.
Well, Juno's instruments and camera were turned off 5 days ago to protect them during this maneuver. That means there will be no new pictures tonight.
The spacecraft went into a safe mode. What that means is that the spacecraft, it's like a smart robot, has a very smart computer on it, detected a condition that was not expected. It did exactly what it was supposed to do when it detects a condition that's not expected, is it evaluates the situation and then takes an action. In this case, it turns off unnecessary subsystems. It points itself, and if not already pointed, to point at the sun, go power positive, link up the communications to the Earth, and then wait for direction and for the humans back home to evaluate the situation and decide what the next forward step would be.
All of the science instruments were turned off about 4 days ago, and right now in our pass by Jupiter for JOI, we're not going to get pretty much any science information at all.
The situation at this point is where we just passed through Jupiter, and the impact was that we shut down our science instruments in order to make sure that nothing unnecessary was being done on the spacecraft as we went by Jupiter. This was the first flyby of many, and in fact this was really just a test. It wasn't even in our plan. We were just kind of going by so that we could calibrate and make sure we understood how the instruments worked and evaluate the environment. But the data was so rich, it's really whetted our appetite and given us incredible excitement about the things that are going to come in the future flybys. Now that was part of a plan prior that we were on this particular orbit we were going to fire our rocket motor. We call it period reduction maneuver, PRM. And what that was going to do, it was the same rocket that we used at Jupiter orbit insertion. It was going to slow the orbit down even more as we passed by Jupiter and change the orbit from being 53 and a half days long to 14 days. And then we would be going around Jupiter every 2 weeks. And after, when we were preparing for that, we detected as we were pressurizing the propulsion system, basically, we were turning on getting ready to fire the rocket, we noticed a different condition in the valves that actually open up and pressurize the system. They behaved with a little bit of delay, which meant maybe the valves were a little sticky.
Back on Earth, NASA engineers scrambled to fix the problem.
There were attempts to jolt it open. They thought perhaps it had just gotten stuck. There were attempts to, kind of go up and down, to try to get it to open.
We didn't want to take any chances that some adverse type of condition would cause the burn to go in a way that we didn't expect. And so we decided to postpone and delay that burn. And at that time, we did it early enough that we were thinking that we could turn this flyby into a science pass and get some science. And of course, the spacecraft safe mode condition eliminated the science. You can think of it as just a plumbing system that's had a little bit of unexpected behavior to it. So we will go in and analyze that, and then once we figure that out, we'll decide where to go next. We're in no rush to make any of these changes. Fortunately, the way we designed Juno in the orbit that we went into was very flexible. It allows very flexible science. So the science that we get on Juno, all of the goals and objectives tied to the scientific investigation of Juno, are really related to the details right around perijove. Each pass has the same value that a 14-day orbit would have passed. We were changing to 14 days primarily because we wanted the science faster, but there was no requirement to do that. So with that, I'm going to go on to the science.
What we can't do is see through the clouds to see what else is there. And we've known that for a long time now. I don't know exactly how long, but it's decades, maybe even 100 years.
We've been measuring via the radio emissions we get from Jupiter for 40, 50 years, ever since it was first discovered.
65 years.
Okay, Frank. 55. For a long, long time. And so it's very precise.
We've got a suite of instruments that's never been assembled to look at an outer planet, different wavelengths, and we're going to probe beneath the clouds, and hopefully we'll understand the weather.
Right.
One of the investigations on Jupiter is called the microwave radiometer. This instrument was basically invented for Juno. This is the first time this instrument has ever been used. Nobody's ever created an instrument like this.
In war research at the MIT Radiation Laboratory, he had invented this gadget called the microwave radiometer. He had traveled with it to Florida to study the effect of atmospheric water vapor.
And its primary objective is to look at Jupiter's atmosphere and see beneath the clouds. And that's what it's helping us see the invisible.
It's funny because a lot of the time, because what we do is abstract and it is invisible, there's a sense of people thinking it's less real or less, but our if you've seen an optical illusion, what you see is so likely to mislead you.
This instrument's capable of basically peeling those layers back as if Jupiter was an onion, right? And I can peel off the layer of that one by one of the onion and see what it's like inside. And so I'm going to show you for the first time an artist's conception based on our data to see what Jupiter looks like underneath. Okay, so here's Jupiter from a visible cloud, the visible clouds that you would see from a normal color camera. Okay, so this is what Jupiter looks like to most of us. It's all recognizable. Here's the great red spot. Okay, so you see these zones and belts, the orange and white and gray stripes. And as you look down to the next level, that's our first high frequency receiver, and then each level goes to the longer and longer wavelengths until I see all the way down. The first thing you can see from this is that the structure of the zones and belts still exists deep down in Jupiter. So whatever's making those colors, whatever's making those stripes is still existing pretty far down into Jupiter. So that came as a surprise to many of the scientists. We didn't know if this was very skin deep, you know, just a really thin layer, or whether it goes down.
So if I could have the next shot. This is a cross-section, a wedge shape of what we think the interior looks like. And you see that onion skin on top, that's the visible surface of the atmosphere that we're familiar with. And if you take a little chunk out of the topmost piece, that gives you the wedge to the right. And that's the region at top that the MWR can probe. That's the convective region of the atmosphere. It goes down to about 1,000 bars.
I'm not sure I can say anything at this point about what causes those bands. It may be chemistry or composition, but whatever it is that's causing that is present at the deeper layers. And although it's evolving, so you know, whatever's tied to creating those bands is being twisted around by the dynamics to some extent, and allowing those bands to move or change and evolve a little bit as we go down to deeper layers. I don't think I can say anything about whether the bands are created in those layers or somewhere deeper down and then transported up. I mean, that's something we may be able to investigate in the future.
But an entry probe into a Jovian planet, that is a conceptual novelty, and there we'll no longer have to deduce from chemical equilibrium where the clouds are. We will pass through the clouds. We will be able to see the particles and the dilution of sunlight. We won't have to guess what the chemistry, and especially the organic chemistry, is. We'll have actual data.
Now, we get down with our longest wavelength, our lowest frequency channel, penetrates down to some of the information it's getting coming from a pressure of 1,000 bars, 1,000 times the pressure here on the Earth.
The other thing that is surprising and very interesting about this is that they're evolving. They're not staying the same. They're changing as we go down, and you can see that by the fact that this one changes as we go down, and actually it becomes less apparent way down, but it still starts moving around. Some of this white is orangey down here, and then this one seems to disappear, and another belt goes down here. So deep down, Jupiter is similar, but also very different. Okay, so this particular instrument gets to see beneath the clouds. So if we were flying by Jupiter and you had X-ray vision, you might be able to see beneath the zones and belts and the beautiful stripes that Jupiter has, and even see how deep are the roots to the great red spot and things like that.
This has got to be one of my favorite images in all of astronomy. Not because of the red spot, but also because all this turbulent flow along here. It's just the gorgeous dynamics that happen in Jupiter's atmosphere. Now, the Great Red Spot is a storm that we have seen for at least 200 years.
That Great Red Spot there is bigger than the whole Earth. In that picture, it's about twice as big as the Earth, but if you took a picture today, it would be more like 1.5. It's been shrinking. It's been around for hundreds of years, and we're getting to see it shrink now. If we're lucky, you and I might be alive in time to see it disappear. It'd be really interesting.
The red spot around Jupiter, what is that about?
Well, that's probably the most beautiful visible feature on Jupiter, and it was discovered 300 years ago. So it is a permanent feature.
Yeah, by Galileo. Yes.
Not. About 50 years later.
Yeah.
Oh, is it? 1664, I think.
Yeah.
Is the date on that.
Voyager's cameras afforded scientists spectacular close-up views of the Great Red Spot.
The red spot is red because of the chemicals that are trapped there in the center of the red spot have been baked and cooked by ultraviolet light and have turned red.
We released this image showing you how the Great Red Spot has changed from 1992, then this first image, all the way down through I think it was 1999 when this image was released. And it's sort of an artistic presentation of the images. Oh, actually it's a cheat, because The image of Jupiter in the background isn't a full image. It's actually got a huge chunk cut out of it. So the reason why we had this beautiful artistic foray of the Great Red Spot was just actually to cover up the fact that we didn't have a full image of Jupiter.
When will we get the first images from Jupiter?
Yeah, we turn the instruments on just a couple of days later, but I'm not sure what the schedule is to send down the first image after that happens. We'll have to get back to you on that.
Okay, I'd like to jump to another instrument, which is the Juno cam, which is our visible camera. And if it was used, it would take a picture of Jupiter that looks just like this. Except we used it when we went over the pole. We got some pictures like the other one as well. But here's the first picture of Jupiter's poles that we took on August 27th. And this was pretty remarkable because it told us right away some things new about Jupiter's atmosphere, and in particular the polar. Juno had its camera, Juno cam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises in them. It didn't look like we thought. It doesn't look much like Saturn's pole. The second is you see many of these cyclones around, and that was kind of a surprise. And then lastly, what I'm going to focus on right now is as we came across, we're always flying over the terminator. That's our orbit. It's called dusk dawn. So we fly around the terminator, which is where the sunlight stops, right? That's what this shadow is. Jupiter's always half lit. So we're flying right across this. And when we look down, of course, when you see something on the terminator, you can see topology. Or, you can see the 3D effects a little bit. So when I give talks at schools, if kids are saying, I got a pair of binoculars or I have a telescope, what should I look at? I always say the first thing you should look at is look at the moon and look right at the line, the terminator, where the light and shade are. Because that's when you can see the craters and the moons. You're seeing topology, right? You can see the 3D effects.
Let's go on to what the word topology means. So, topology, what is it? It's the study of things that remain invariant, unchanged when you do deformations. So here is a picture of what do I mean by a continuous deformation. Well, I take a thing and I squish it and I scrunch it and I pull it, but I don't rip or tear it. And I want to ask what remains the same. Well, if you like, the fact that there's a little hole that I could sort of go through here between her back and her front.
Because that's when you can see the craters and the moons. You're seeing topology, right? You can see the 3D effects.
What is topography? Topography is the study of a land's surface shape, its hills and mountains, valleys, rivers, and craters. Topographers analyze these features, whether they're on the Earth, the Moon, an asteroid, or on a distant planet.
Because that's when you can see the craters and the moons. You're seeing topology, right? You can see the 3D effects. We're seeing, for the first time, the 3D effects of Jupiter's atmosphere. And I can show that to you. And this came as a surprise to us as well. Right here, this one cyclone shows shadows, which right away told us this part of that storm system is elevated above Jupiter's base atmosphere. Now, if you were to ask me why didn't I think of that before, I would say I should have. Now, here's a close-up of that shadow, and you can start to see the shape. And so what's amazing about this shadow is so we've done some calculations based on this first image, and this shadow, or this cyclonic storm is about 7,000 kilometers across. So that's more than half the size of the Earth. And its elevation, based on our estimate of this and looking at the shadow and the rest of the geometry, is that it's vertically towering up about 85 kilometers or more. And so you can imagine the kind of atmosphere you're dealing with. If you were at Jupiter and you're flying a plane through it, or unlucky enough to be in a balloon, and you're looking at a thunderstorm or a tornado that is half the size of the Earth and 100 kilometers tall. So it is a truly towering beast of a storm, probably the biggest thing we've ever seen. And so this is what Jupiter is really faced with. Now, JunoCam, one of the things that's interesting is JunoCam is an outreach camera. We put it on in order to connect to the public, but it clearly has science value, and we're already reaping that.
Thought that we would do some science with JunoCam, but because it's one of the main goals is to do the outreach, what I have told my colleagues is that if they want a picture of a particular storm or belt or zone, they need to put a point of interest into our database. They need to discuss why it's important, and then they have to round up the votes when it comes time to vote.
So it's called JunoCam, and it will take great pictures of the poles of Jupiter. It's sort of designed that way to be able to get pictures of that polar region in the north and south where we don't have any good pictures. But it's also designed, and the way we're using it is designed to do what we're calling science in a fishbowl.
But it is primarily aimed at reaching out to the public and allowing the public to get engaged and process their own images and get involved in science, and also to do some artistic work with it. And we've already gotten that. You can go onto our website. You can see posted images that are raw. The public can process those, post them. Sometimes they're scientifically interesting. Sometimes they just make an artistic gesture.
So we also have a camera that's called JunoCam, and it's a public outreach camera.
What we are doing with our little ops team is we are staging the raw data from JunoCam. Anybody can download those images and they can do anything they want with them.
The basic idea is we want to do science out in the open with everybody who wants to participating and seeing what's going on and being part of it.
And so what I'm going to share with you are some of the really fabulous products. This happens to be one of my particular favorites in the color choice selection that this person made. Here's a fun one. Does everybody see the happy face? The two eyes and the big smile? This is a reflection. Basically, this person mirrored the South Pole image to get the eyes and the smile. Do you recognize this one? Van Gogh's Starry Night? This is Juno's Starry Night.
The Voyager views were so stunning that we forget how crude they were in some sense, is that they were mostly global views with the resolution of a kilometer or a few kilometers. That's equivalent to a global meteorological picture of the Earth from a weather satellite, which is great for looking at some things, but you can't see much detail down there on the ground. With Galileo, we go from that perspective to the perspective of something with Landsat resolution. That's going to be a real eye-opener for people interested in the geology of the planet.
To command just the electronic camera that makes pictures of Jupiter, Pioneer Control transmits some 15,000 commands in just 2 months. In response to these commands, the camera scans Jupiter's turbulent cloud tops as Pioneer spins toward encounter. First, the scans are built up line by line on a television display. This gives a quick look at the operation of the system and a tantalizing hint of the spectacular pictures buried in the raw data. After the first stage of prettying up, Jupiter's first close-up portrait emerges. His studies have produced some of the most outstanding color photographs ever made of Jupiter from the Earth's surface.
This is sort of a typical photograph which shows the red spot of the planet, which is the most prominent feature. This black spot here is the satellite shadow.
This is the largest operating telescope that has ever been built. With this telescope, the planet Jupiter appears of the size of a 50-cent piece.
Jupiter, largest of the Sun's 9 planets, was photographed close up by the Voyagers 1 and 2 spacecraft. What their camera eyes recorded as they passed by the giant planet's churning clouds were ribbon-like streaks of red and brown and yellow.
It worked. We're traveling at about 39 kilometers per second after the Earth flyby, which is fast, obviously.
Juno becomes the fastest artificial object in history. And before it leaves Earth forever, it captures a unique video.
For the first time, a movie was made of the moon and the Earth.
Two television cameras are the eyes of the spacecraft. They can be aimed with great precision. September 18th, 1977. Voyager is 7 million miles from Earth. Its cameras turn back to record the blue Earth and crescent moon together. "14 months later, Voyager 1's cameras transmit the first photographs of Jupiter. February 5th, 1979. From a distance of more than 17 million miles, Jupiter and 3 of its moons are caught in a single frame. At 12 million miles, Jupiter's clouds of gases and ice particles are seen to swirl and twist in strange new patterns invisible from Earth.
So what you're seeing actually is the first time that humans in any time in history have actually been able to see the motion of the heavenly bodies. I mean, this is how nature works. We've never actually been able to see it. This is what Galileo realized. He realized, oh my gosh, that means they're going around Jupiter. And of course that changed our culture forever, because all of a sudden you had Earth wasn't the center. Here's something else that's got things going around it. That was a very profound moment for our culture. It changed us, our perspective on even ourselves and how we fit into nature. And now, 400, 500 years later almost, we're able to actually see the motion ourselves. This is the first time. We haven't even got a movie of any planet and moon together. And so it's great that Juno was coming in at this angle and had the right kind of camera to capture this motion. And that's really what it's about. Nature is that way. We only have a few senses. And what we've learned over this studying things for many years is that we can extrapolate those senses, and we can also make up new things, and the universe is full of those things. It's not all about us. I mean, Galileo, when he looked out and said, oh my God, there's something else going around Jupiter, we're not the center, that idea permeates everything in a way that we can interact, see, or even communicate with everything in the universe. We've started to learn that. We have to build special machines to do it. And then we figure it out. Some brilliant person theorizes something that nobody's thought of and figures out that we ought to go look for this, and then goes and builds a giant collider, and lo and behold, they find it.
We're working in a new environment, which we don't know the physics of how things work at these high pressures, and they're coming up with theoretical quantum mechanical models, but they can be wrong. And so we're going to make the observations that will be key, they will be important. But I'll bet you that the theorists are going to keep adjusting and adapting their models, but we will have constraints.
Are there any plans to take images of Jupiter's cloud tops?
The answer is yes. We did actually take some pictures at Perijove on the last flyby, but what we found was that we had not set our exposure settings to long enough. We're taking pictures of a cloud right near the shadow. So in a lot of ways, that was a test run for us, Perijove 1, and so now we know, how much we have to boost our exposure time. So
the first flyby on August 27th was not really part of the science mission. We had all the science instruments on, but what we wanted to do was test them, calibrate them, make sure we understand how they work close to Jupiter. And originally this flyby that happens today was designed to actually change the orbit. And when we opted to go ahead and put on these science instruments, it was still sort of to just get extra science.
You know, I forgot to say something I want to add. We took a real leap of faith with this experiment with the public.
The data that we collected on PJ1, as Candy pointed out, was really a test case. We were using that time to test out exposure rates for the cameras, what are the right ones to use. We've never been this close to Jupiter, and all of the instruments had some aspect like that. Obviously, most of them got great science. You saw these incredible images that we got. I just showed you the microwave data. Each data set is remarkably, unique and discovery-like. We are seeing things that we didn't expect across the board. The magnetic field, the aurora, the gravity field, every one of them have produced outstanding new science results.
When's the camera going to turn back on, and when can we start seeing rapid release of the raw images?
Yeah, I mean, we thought we would have some today. There is a piece of spacecraft data that we have to wait for to complete the initial processing that has to do with the rotation rate of the spacecraft. So that is like 2 days. So our plan on every Perijove is that as soon as we get that spacecraft data, we start posting our images. So there's no holding back or validating or anything like that. They'll go right out as soon as we have that last piece. Now, obviously, we won't have any going out. It would have been Friday of this week. At the next Perijove, however, we will plan to take images. One of the things that we learned from the first Perijove flyby is that it's very important to get context. So we will take a series of images as we're approaching the last 10 hours, and then we will do a series through the Perijove Pass, and then for a few hours afterwards. Now, we've been debating about putting that out for a vote because we're not really quite done with our testing. Because of some of the things that we learned at Perijove 1, we want to try some new things the next time we image. But we probably will put maybe half the data volume we'll allocate to be chosen by vote and reserve half for testing. But that's not our plan going forward. Our plan, as soon as we've figured out how to really get the best out of the camera settings, then we will have it all by public debate and voting.
The images it took were thousands of times more detailed than any taken before. Then, 2 months out, there was a disaster. The tape deck used to record the vital data jammed.
What they discovered was that this tape recorder, if it was run at very high speed, was prone to the tape actually getting hot and sticking.
And so we re-engineered the mission so that we would only use the slow speeds of the tape recorder, and we didn't use the whole thing. So that, coupled with the antenna, really limited the amount of data and how fast we could send the data back to the Earth.
Unfortunately, the antenna is crippled. It did not deploy successfully, and it will be a month or more before we're able to download a single picture.
So if we can run this video. Reminder, this is a pre-impact video just to show you the amazing quality of the images from the Hubble Space Telescope after its refurbishment mission.
So what we're trying to do as scientists is get beyond that, to get under the surface of these things we see in our daily lives and see where our intuition is right and where it's failing us.
Well, in fact, I think scientists, because they're studying this, and you're studying magnetic field or a gravity field or some particle you can't see, they're studying, or just ultraviolet or infrared or X-ray light, things that we've extended from, that we can't see with our senses. Because you're a scientist, you're starting to study this, you get used to it. In the same way that when you're an infant or a kid, you get used to wind, sound, and odor. The scientist doesn't think anything of these invisible fields because they're used to working with them.
We'll fly in close, we'll dive underneath the radiation belts and out the other side. And we'll fly through the charged particles that bombard and light up the atmosphere with the northern aurora. So let me talk a bit about the Jovian aurora. If we could have the picture here. This is a Hubble Space Telescope picture looking in the UV, the ultraviolet light, at these blue, they look blue, but it's ultraviolet in fact. So let's have this movie of the aurora that was taken in the past month.
And so when we actually get used to it and if we're familiar with it, it doesn't mean we're seeing it or experience it with our senses. It means that it's a concept that we know exactly what happens as a consequence of those assumptions that we can think about, even if we're not seeing it.
I think you become comfortable with its existence in the same way that we're all comfortable when we go outside and the wind exists. I'm comfortable with the idea that the Earth has a giant magnetic field and it's doing something to charge particles that I can't see because I've gotten used to the idea of because I've studied it for so long. And to somebody that hasn't studied it first hears it, it sounds very abstract and it sounds odd. And what I'm trying to communicate here is that, you know, you've gotten used to other weird things. If you read enough about this, you'll get used to this too.
There have been other missions to Jupiter before. There was Pioneer, Galileo, but unlike the others, Juno is solar powered.
So we have solar arrays that are tested and specifically designed to be able to last through the cold temperatures and the high levels of radiation. They have a cover glass on them.
Pioneer gets its electricity from small onboard atomic heat sources. At 500 million miles, the sun is too weak to power solar cells.
As technology advances, we do see more and more. And it's not just true for physics, it's true in biology too, that until you have the tools to see things, no one guesses them correctly. Even blood cells, you looked under a microscope, or
That's right.
DNA, you had X-ray diffraction. And it's the same for the physical universe. And so you develop so you think, you know, it would be nice to think we could just predict it all, or we could just know it's there. But the fact is, until we actually test these ideas, we don't know. And so so science advances as a combination of technology and interesting theoretical ideas. So people wanting to think about things, but people also wanting to see them, and not directly with your eyes, but see them by measuring that they're there.
What I'm going to show you now is some exciting new data that we just got last week. Can I have that animation? So what you just crossed was what scientists call a bow shock. It's the same kind of thing that you hear about if you're on listening about how a supersonic jet works, right? It flies through the fluid or the air and makes a shock in front, a shock wave.
In March of 1979, nearly 2 years after launch, the Voyagers approached Jupiter. Passing through the boundary where the supersonic solar wind slams into Jupiter's magnetic field, the spacecraft's instruments recorded a strong bow shock.
So Juno does other kinds of science. I mean, besides the recipe and this magnetosphere crossing, what we're really after with Juno is the ingredients. From the ingredients of Jupiter, we're going to figure out the recipe. And that's what's going to tell us how planets are made. You know, what Juno's really about is learning about the recipe for how solar systems are made. Scientists don't really understand how the planets are made.